Okay, so here is a table of standard electrode potentials. So we've got E theta here. The theta sign means they're under standard conditions, which we'll go through a little bit in a bit. Also known as reduction potentials, because if you look at all these equations, they're pointing left to right, as they always do, but they're gaining electrons on the left-hand side, so they're all reduction reactions. Now actually, any of these reactions pretty much can go in either direction. So you sometimes see them with equilibrium signs. But the true definition of them are the standard reduction potentials, or we just call them electrode potentials. It's quite a mixture of different things here. We've got alkali metals at the top here. Alkali metals like to lose electrons, as you know, so these ones at the top probably go backwards, depending on what they're connected to, but they're most likely to go backwards. And if they do, they lose electrons, hence becoming oxidized, and they're reducing something else. They're good reducing agents. If we look at the other end of the table, things like fluorine is very good at gaining electrons, and if it does, it becomes reduced, hence it's a very good oxidizing agent. There's a whole mix of things in here, metals, non-metals, some just ions, see, I mean this one here, you've got gas and ions, nitrates, we've got here Fe3 plus going to Fe2 plus, so a real complete mixture of different things. These are all these equations are half reactions, and they can all occur in half cells, so it'll be 1/2 of a cell. Now depending on what kind of species we've got here, we'll have slightly different type of cells each time. So there's 3 main types of cells that we'll look at. We'll have a look at those now. So probably the most basic one, which you've already seen, is the metal-iron half cell. In this case, the metal, and it does have to be a metal because it must conduct, it must be solid, takes the form of the electrode, and the ions are in solution. Any ions in solution must have a concentration of 1 mole per dm cubed for them to be in standard conditions. This one is a non-metal ion, so it's chlorine. Now chlorine, as you know, is a gas. It's gaining electrons to make chloride ions, which are aqueous. So a gas and aqueous ions obviously don't make good electrodes, and they're not neither of them are metal. So we have an electrode made out of platinum. The platinum's unreactive, so it's not going to really take part in any reactions, but it will allow electrons to pass through it. It does conduct. So the chlorine gas would have to be pumped in here, standard condition of 1 atmosphere. This would be like a glass tube to make sure the gas goes in the right direction, basically. And then the chloride ions are 1 mole per dm cubed in solution. And therefore, at the interface of electrodes, you have both parties you need from the half equation. This one is, we've got 2 ions. So you've got Fe3 plus and Fe2 plus. Now, neither of them, although metal ions, neither of them are actually solid metals. So you can't make an electrode out of them. So again, you use a platinum electrode. This line sticking out here is just a wire each time. So the platinum electrode, again, is unreactive. And the ions are in solution, and they both have to be 1 mole per dm cubed. So these are half cells, and all these half cells, as we saw, have these numbers which we call standard electrode potentials. So let's have a look at what is a standard electrode potential. Well, it's a definition you need to know. The standard electrode potential is the EMF, and that's another word for volt, another way of saying voltage, of a half cell connected to a standard hydrogen half cell under standard conditions of 298 K. Solution concentrations of 1 mole per dm cubed and a pressure of 100 kPa, or you can say 1 atmosphere. So you take the half cell you're interested in and you connect it to the standard hydrogen half cell, which is interesting because if you look back here, hydrogen connected to itself, this voltage would be 0, wouldn't it? Okay, that 1 volt is the standard hydrogen half cell. So let's have a look at an example. Let's see how they would have got this number here for fluorine. So here's the fluorine half equation. There's its standard electrode potential. But this is the setup they would have used. This is the standard hydrogen half cell here. It's got this half equation. The H plus ions gaining electrons become hydrogen gas. Because it's a non-metal ion, you've got the platinum electrode. You've got this glass cylinder, so the gas can be pumped in. You've got your H plus ions of 1 mole per dm cubed. Okay. And on the other side, as we look at fluorine, similar thing, isn't it? Fluorine, 1 atmosphere coming in. Fluoride ions, 1 mole per dm cubed in here. And again, this will be another platinum electrode. Got to have your salt bridge. If you do that, that will give you the standard electrode potential. So that's how all these electrode potentials are derived. They're from actual experiment where the half cell has been connected always to the standard hydrogen half cell, and we always compare everything to the standard hydrogen half cell, and that gives us our standard electrode potentials. Cells don't have to have the hydrogen half cell. Okay, it's only when you want to work out the standard electrode potential, because the standard electrode potential definition states that it's connected to the standard hydrogen half cell under those conditions.